Absolute extrema. The extreme value theorem with corollary. The extreme value theorem says, if f of x is continuous on the closed interval a to b, then f of x will have an absolute max and an absolute min value on that interval. The corollary to the extreme value theorem states that the absolute extrema will occur at either a critical point or an endpoint. We'll see in just a little bit that is the corollary is what we tend to use when we prove problems or solve for absolute extrema. Let's get a little bit of intuition first to see why this works. So I'm going to draw a quick sketch of maybe a couple graphs. What if I draw the graph f of x? I'll just draw it like this. It has an endpoint, I'm continuous, and I have something like this. Just by looking, where are the highest and the lowest points on the graph? Well, in this case, the highest point, which is my absolute maximum value, occurs at an endpoint. How about the lowest point, which occurs right there, the absolute min? Notice this is when my derivative is 0, so it occurs at a critical point. I could draw another graph to show something similar. What if I have a graph like this? I'll call this g over here. It's going to be continuous. Now, where do the absolute max and the absolute min occur? Well, the absolute max is at a critical point, and the absolute min is also at a critical point. So the highest and lowest points on any graph must occur at a critical point or an endpoint. Now, why can't it occur when, say, f prime equals, say, 2? Why can't I have an extreme value, an absolute extrema, when f prime is 2? So right about there, I would say f prime is maybe 2. Seems reasonable. Notice that right around it, though, there is a value that's higher than that, and also a value that's lower. So convince yourself that this corollary must be true. That is, absolute extrema will occur only at critical points or endpoints. So I want to start by showing you the typical way that we determine absolute extrema. By far the most common way, but not the only way. And we follow this process. We're given the endpoints, generally speaking. So the first thing we want to do is find our critical points. Why do we want to find the critical points and know the endpoints? Because those are the only places where the function can have the highest and the lowest values, the absolute max and the absolute min. So we're going to take those critical points and those endpoints, and we're going to plug them into the function. And we're going to get the function value at those points. The largest of those function values is the absolute max. The smallest of those function values is the absolute min. Let's take a look at an example. So let's consider the function f of x equals 3x squared minus 12x plus 1. And we want to find the extreme values. That is, we want to find the absolute max and absolute min values. And I'll abbreviate max and min. And let's say we have the interval, let's make it 0 to 3. Since f of x is a polynomial, I know that f is continuous on any interval. So we have the conditions where we can use the extreme value theorem and its corollary, which says we need the endpoints. We have them 0 and 3. We need the critical points, where f prime is 0 or undefined, but again, polynomials are smooth, so polynomials never have undefined derivatives, which means we only really care where the derivative, 6x minus 12, equals 0, which is at x equals 2. And now we're going to take those values, we'll take the endpoints, f of 0 and f of 3, as well as the critical point, f of 2. And we want to find the value of the function at those points. I left a space on purpose. We'll see why in just a bit. So f of 0, pretty easy to find, is 1. F of 2 is 12 minus 24 plus 1, which is negative 11. F of 3 is 27 minus 36 plus 1, so negative 8. What is the absolute max value? It's easy to see. It's 1. How do I know? Because it's the biggest of the values that I have. And I know that the absolute extrema must occur at one of these points, an endpoint or a critical point. What is the absolute min value? Again, I can simply look. Which one of these values is the smallest? Negative 11. Now, a lot of students, when they're doing this, they have 0 and 2 and 3 that they need to plug in, so they think, well, I should probably also plug in x equals 1. But if you do this, you are stating to your professor or whoever is grading that you do not understand the extreme value theorem and its corollary, which says extrema can only occur at endpoints and critical points, which means I should only be checking endpoints and critical points. Let's take a look at another algebraic example. Let's consider g of x equals, say, the sine of 2x minus x. And let's do this on the interval 0 to pi over 2. We have our endpoints, 0 and pi over 2. We need our critical point, where a derivative is 0 or undefined. But again, both sine and x are smooth and continuous functions, so the derivative will always be defined. The derivative of sine of 2x is the cosine of 2x with the chain out, so 2 cosine 2x, and then minus 1 equals 0. So what we're trying to find is when the cosine of 2x equals 1/2 to get our critical points. Well, the cosine of 2x equals 1/2 when 2x equals pi over 3 or something else outside our interval, so I'm not going to worry about it, which means x equals pi over 6. And pi over 6, just to kind of get a value, is pretty close to 0.5233. So it's about, because we're going to need some, and I'll just put 0.523. We're going to need some decimals in a little bit. Because we need to find the function now, not the derivative, but the function at the endpoints, 0 and pi over 2. As well as the function value at the critical point, pi over 6. Let's start by finding g of 0. So we have the sine of 0 minus 0, which is 0. Pretty straightforward. Now for g of pi over 6, we have the sine of pi over 3, which is root 3 over 2, minus pi over 6. And if we get an approximation for that, we get a value of about 0.343, assuming I type things incorrectly. And then g of pi over 2 is the sine of pi, which is 0, minus pi over 2. And I'm not going to get the value for that because I see that I have one of my potential values is 0, one of my potential values is positive, and my other potential value is negative. So the absolute max value is that one, the only value on that interval at those points that is positive. And the absolute min value on this closed interval is the only value that's negative. At least of the choices that I have. Let's look at one somewhat atypical problem, or kind of, maybe I should say a less typical problem. So we can only give like a reasonable answer for something like this. That is, we can't really prove an answer, but we will be able to a little bit later in the semester. And let's call this f prime. We're not going to find the values, but I want to ask at which x values. So we're not going to find the function values, but we're going to look at the x values. So at which x values does f, that we can't see, have an absolute max and min, which I will abbreviate as absolute max and then, or abs max and then abs min. So how do we know? Well, I still know that absolute extrema must occur at endpoints or critical points. So it must be at x equals 0, or x equals b, or x equals d. Why is it not x equals a or x equals c? Well, does f prime equal 0 there? Or does f prime equal 0 down here? The answer, of course, is no. Those are not critical points of f. So the absolute max and min must occur at one of these places. So how do we determine which one is the biggest and the smallest? We're going to give a reasonable answer, not a proof again, but hopefully one that makes sense. So let's look at the first interval, say 0 to b. Notice that f prime is positive, because we have the graph of f prime, which means that f is increasing, but not a lot, right? I'll put not a lot. It increases, but increases a little bit, because f prime never gets big, and we don't have a very long interval. How about on the interval from b to d? On that entire interval, f prime is negative, which means the function is decreasing, but it looks like it's decreasing a lot, at least in comparison, or relatively speaking, to how much it increased. So if I were to draw a graph of f, and I don't know a starting point, so I'll just put it at the starting point is at 0. It looks like the graph increases a little bit, say up to b, and now it decreases a whole lot, all the way to d. Is it obvious by the picture? Notice that is a picture of f, where f has its biggest value. It's at x equals b, isn't it? And where does f have its lowest value? At x equals d. Once again, extreme values will only occur either at critical points or at endpoints.